Right, let's start. So in the last class, I just introduced the Lempel-Ziv class of algorithms. So recall that our objective was to design a universal compression scheme that gives us something which achieves the entropy rate kind of without estimating the probability mass function. Right? So even without, say, computing the frequencies or explicitly estimating the probabilities of the various symbols, we want to design a compression scheme that still achieves entropy or entropy rate. All right? And towards this, I started introducing the Lempel-Ziv 77 class of algorithms, which worked in the following way. So at the heart of these Lempel-Ziv algorithms is the following parsing. You take a string and then you parse it into a sequence of substrings, which we'll call phrases. All right. So for example, this is one partition of or one parsing of the substring into phrases. All right. And how do you do the parsing for the Lempel-Ziv 77 algorithm? Basically, it functions in an iterative manner. So if you have parsed up to x1 through xt, then the next phrase is basically, if there is no match, then it's just the next symbol itself. If, please settle down. So the next phrase is equal to the longest match from xt plus 1 up to some xt plus k, which matches some substring that is present in the history or the context. All right? So it is the longest possible match of the future given the history. If no such match exists, then the next phrase is just the next symbol itself. All right? And we saw a couple of algorithms. Again, just to refresh our memory, let's look at another example. What would be the parsing of this particular string? Yeah? The third one, just the third one. So this particular example here. What would be the first phrase? A, the next phrase, B, next, C, and everything beyond that, right? Okay. Any questions? All right. Okay, so this gives us parsing. So we've decomposed the whole string into a sequence of substrings or phrases. How do we encode each phrase? So what we want to do is, given an encoding of each of these phrases, we should be able to reconstruct the entire string. Right? So what are the components? What are the basic components of each phrase? So each phrase is either a symbol that has never been seen in the past, or it is something that matches some substring in the past. So if it matches something in the past, then all you need to do is mention where it was present in the past. Right? Because suppose that you have already recovered the entire context. If the decoder knows the context, then all it needs to know is where in the past the substring matches. So there are two components that you need to specify. What is the location of the starting point of the match, and what is the length of the match? If you give this much information, then you can recover the next phrase given the context. All right? And if there is no match, then you need to specify what the next character is, because you've never seen this character in the past. All right? And just to distinguish between these two cases, we'll have an additional flag bit. So if the flag bit is equal to 1, then it means that there is a match. If the flag bit is equal to 0, then it means that there is no match, and you need to specify what the next character is. All right? So again, let's go back to the example. ABC, 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 and so on. We know that the parsing is A, B, C, and then everything else, right? So how would you encode this? Right, so the first phrase is just A and there's no match. So the flag bit is set to be equal to 0, and you need to specify what the character is. What about the next? 0, B. The next encoding? 0, C. And what about the next? So it's 1 because there is a match. And now I need to specify the location of the match. And the location is specified in a relative fashion. So assuming that this is the starting point, you need to give the pointer to the starting location of the match, which in this case is 3 symbols in the past. All right, and that is equal to 3. And what is the length of the match? So if the sequence has length n, then what is the length of the match in this case? N minus 3. All right, so this is an encoding. All right, so the compression scheme is basically the encoding represented in a succinct manner. So let's see, there are essentially 4 components that we need to encode. One is the flag bit, which is easy, it's just one single bit to represent the flag. Then the character, a new character. So if you know the alphabet, then that character can be represented using log cardinality of x number of bits. And there are 2 more components, which is basically the pointer to the start point of the match and the length of the match. And both of these are integers. All right. And in this particular example, we see that these integers can be pretty large. In this case, the size of the match or the length of the match is n minus 3. Okay. So to represent the flag bit, you need 1 bit, and to represent the next character, we can do that using log cardinality of x bits. And now I have the pointer and the length of the match. How many bits should I allocate, or how should I represent these? Because these are both integers. They can be as small as 1. They can be as large as order log n. Order n. Right? So any suggestions? How would we go about this? So firstly, would it be wise to represent these 2 integers using fixed number of bits? What do you think? So do you get the problem? Do you get the question?
The repetition can increase our maximum, like the length of the sequence.
Correct.
Can be longer than the maximum number you can represent.
Correct. So the question is, well, the largest, both the pointer and the length of the match, they can be as small as 1 in each case. The pointer can be 1 because it could just be 1 symbol in the past, the starting point of the match. The pointer could also be as large as some constant times n, because maybe the location of the match for perhaps the last phrase could be somewhere in the beginning of the string, right? The same thing can happen for the length of the match. It can be as small as 1, but it can also be as large as n, right, or very close to n. So if you had to represent all of these using fixed number of bits, then basically you would need to allocate log n bits for each of these, right? Would that be wise? No, because then you would not get any form of compression, right? Because suppose that the number of phrases is something that grows maybe linearly with n. We don't know how large it could be, but let's say that it grows linearly with n, then just this itself would take n log n bits, right? So we don't get compression, it just blows up. So then what do we do? So the strategy is that you represent each of these using variable number of bits. But then how do you do that? In principle, if you had to represent an integer n, you could represent it using log n bits. But the problem is, how do you know what log n is, right? So can we come up with a prefix-free variable length code for the set of integers?
So here,
Yeah.
can you find the property distributions of the pointer and the length of match, and then you can use some kind of conservation inequality in order to minimize the cases where we are not able to represent using those number of bits.
Okay, so the strategy that is being proposed is it possible to essentially estimate, without looking at the string itself, can we say something about the statistics of the pointer and the length of the match, and therefore use, I don't know, maybe design something like a Huffman code or some kind of a coding scheme to say that either these two quantities are never too large, or maybe design a variable length source code for the pointer and the length of the match, assuming that we can say something about the statistics. Now, in general, that's very hard, all right, because firstly, both these quantities would ideally depend on the distribution of the source itself, all right, and without knowing the distribution of the source, you can't really say anything much about the distributions of these two quantities, all right, and even otherwise, even for simple distributions, characterizing the distributions of these two, even for, let's say, IID Bernoulli sources, characterizing the distributions of these two is not too easy. We will say something about these distributions, but finding the exact distribution is hard. All right, so that's difficult to do. Instead, we'll come up with a variable length scheme to represent these two, which is maybe not optimal, but that's okay. Overall, we'll see that the overhead or the penalty that we have to pay is not too much, and the whole scheme still approaches the entropy rate. All right. So here is one such scheme. So what we want is a variable length source code for the set of all positive integers. There are many source coding schemes for integers, and here is one such thing that is good enough. So what we'll do is, given any positive integer, let's say n, the variable length source code will consist of 3 parts. All right. So first, to represent n, we can represent this in binary using log n bits or ceil of log n bits. All right. Let's take an example. Let's say I have the integer 7. Okay. what is the minimum number of bits that is needed to represent 7 in binary? 3. All right, so I'll do that. I'll represent this in binary. And what is the binary representation of 7? 1, 1, 1. All right, so I'll take this. So this is the binary representation of n. Now this has to be a prefix-free scheme. So I need to know how many bits were actually used to represent n. So in this case, there are 3 bits needed to represent n. So I'll represent 3 in binary. Okay. What is the representation of 3 in binary? So using the minimum number of bits, 1, 1. All right. So this is the binary representation of C log n to base 2. That's because I have used precisely these many bits to represent n in binary. Okay? But you run into the same problem, right? How many bits did I use to represent 3 in binary? Right? So 2. But how do I represent this? I'll represent this in unary format. All right? Which is a sequence of zeros. So 2 zeros in this case, let's say, followed by a 1. Okay. In fact, I don't need 2 zeros followed by a 1. I can just represent this using 0, 1. Assuming that I'm using the positive integers. So this would be the unary representation of by a unary representation. So any integer, let's say unary representation of some integer m is basically a sequence of m minus 1 zeros followed by a 1. All right, so this is the scheme. I'm giving you one particular algorithm. So first, are you convinced that this is actually a prefix-free code? Or it's an instantaneous code? Once you read the sequence of bits, you can say that, yes, I have finished decoding this particular integer or symbol. So what is the decoding algorithm? So the decoding algorithm is you start from the first bit, you keep reading until you hit the first one. All right. Once you hit the first one, basically you have recovered the unary represent. So this is the unary representation of some integer. So you have recovered log n. Okay. So you get this number log n. What you do next is you read the next log n bits. Okay. Once you read the next log n bits, you get the value of log n. And you read exactly those many bits. And that gives you n. So let's write that down. So let's say there are m minus 1 zeros. Okay, so you read the first m bits and you recovered and you saw that there are m minus 1 zeros and then followed by a 1. The next step is read the next m bits and convert this to decimal. Alright, so you read the next m minus 1, you read the next m bits and convert this sequence of bits into decimal, from binary to decimal. You get some integer, some positive integer. Let's call this n1. Next, you read the next n1 bits and convert to decimal. Let's call this n, and you output this n. Right, so let's see how this works. Let's say I have 0, 1, 1, 1, 1, 1. Let's run this algorithm on this sequence of bits. So first, what would you do? You start from the left, you read until you hit the first one. So how many zeros precede the first one? 1. So what is m? M is 2. Equal to 2. So now starting from this point, you read the first 2 bits. Starting from this point, you read the next 2 bits. All right. And then you convert that into decimal. You have 1, 1. So convert 1, 1 to decimal, which is 3. So you read the next 3 bits. Now you convert that to decimal. It's 1, 1, 1. N is equal to 7. Okay. Let's see another example. Now suppose I have a sequence of 2 positive integers and I want to encode this sequence. Let's take 11 followed by 3. Okay, so I want to sequentially encode this and then also decode the 2 symbols. So let's start with 11. What is the binary representation of 11 using the fewest number of bits? So it's 1, 0, 1, 1. And this required 4 bits to represent. What is the binary representation of 4? 1, 0, 0. So I'll prefix this with 1, 0, 0. And so for this I needed 3 bits. So I'll represent 3 in unary, which is 0, 0, 1. Okay, so this is the representation, this is the binary representation of 11. All right. Let's now do that for the integer 2. What is the binary representation of 2? It is 1, 0. And how many bits did I need to represent this? 2 bits. So how many bits do I need to represent 2? Again 2 bits, which is 1, 0. And what is 2 in unary? It is 0, 1. Okay, so now I have this stream of bits and I want to decode. So let's try to decode first. So you start from the left and you read the zeros until you hit the first one. So there are 2 zeros followed by a 1. So in this case, what is the value of m? It is 3. So you read the next 3 bits, which is 100, and you convert this to decimal. What is 100 in decimal? This is 4. So you read the next 4 bits, which is 1011, and convert that to decimal, which is 11. All right, so this is the first integer, first symbol. Now you continue from this point onwards. Again, you'll see a unary number. So you read the zeros until you hit the first one. I see 0 followed by 1. So what is this? So this is 2. You read the next 2 bits and convert that to decimal. I see 10. The decimal representation of 10 is 2. And then I again read the next 2 bits, which is 10, which is 2, which is going to be the next symbol. Okay. So you can see that this is a prefix-free encoding of the set of positive integers. All right? It's an instantaneous code, which means that you see a sequence of bits, you know when to stop, and you can decode the symbol uniquely. All right? So this is a zero error scheme. Hopefully, do you agree with this point? Yeah. It is, okay, we don't know what optimal means in this case, all right? All right. But at this point, are you okay with the fact that this is a lossless encoding scheme for the set of positive integers? All right? Yeah.
Is greater than match, length of match.
Huh.
So we cannot identify where the chain gains for pointer and method.
I'm sorry, I didn't get the
Like
question.
for decoding or decoding,
Correct.
we cannot distinguish between where it ends for pointer and length of match.
So in this case, let's say that the pointer was,
It's okay.
correct.
But if pointer is greater than length of match, let's say it is 3 and the length of match is like 11.
Okay.
So,
So-
in that case,
So let's say basically you're saying that I have 3, 11 as the set of integers. Still you can use the same approach, right? What is the binary representation of 3? It's 1, 1. What is the representation of, so this requires 2 bits. So the binary representation of 2 is 1, 0. And the unary representation of 2 is 0, 1. Similarly, for 11, it's the same encoding as before, which is 1011, 100, 001. Now, if I had to decode this stream of bits, I first see the unary representation, 01, which is 2. I read the next 2 bits, which is again 2. I read the next 2 bits, which is 1, which is 3. This is going to be my first symbol. And then again, I read the next unary string, which is 001, which is the integer 3. Read the next 3 bits and convert that to decimal. I have 100, which is 4. So read the next 4 bits and convert this to decimal, which is 7. I'm sorry, 11.
by identifying zeros, unary representation.
Correct. So this unary representation allows you to say exactly how many bits you have to read in the future. All right. Now, so yeah, m doesn't have an upper bound, right? It can be as large as you want. That's okay. So right now, when we're doing this arithmetic, we are assuming that these integers can be, because in the end, if you want to represent, so you're trying to decode some integer, right? If you're assuming that this integer can be stored in memory, then that counter should be able to read up to that particular integer, so that will not be a problem. All right. But one thing that may have already crossed your mind is, look, is this doing any form of compression? We seem to be using a huge number of bits to represent even small integers. All right. But the point is that this is a very inefficient way to represent small integers. But if the integer is very large, then this turns out to be a pretty good representation. So let's count the number of bits that is required to represent any positive integer n. So first, the last part of the representation is the binary representation of n, which requires seal of log n bits.
So if
Yeah.
n has a 2 power, then requires plus 1 an extra.
So n is a power of 2.
Let's say it's 2. So 2 will equal to.
Fair enough. Okay.
But if n is not a power of 2, it is same. So I think it's just like it's lower plus 1.
Yeah, it's maybe better. Bits. Yeah, you're right. So it should be floor of log n plus 1 bits.
So in 311 case, where you represented 11,
Correct.
then after 4, so it's need to be 301, right? After 4,
I'm sorry?
when you represented 311 case above,
Correct. Here.
in the 11, like when you're representing 11,
Yes.
you put first 11 in the binary,
Correct.
and after that 4 in binary.
Correct.
And then after that in the unary,
Yes.
it will be 301.
No. So if I want to represent a positive integer m, I'll represent it using m minus 1 zeros, m minus 1 zeros, and then a 1. Because the smallest integer I will represent is 1.
So here m is 4, right?
No, m is basically the number of bits I have used to represent this particular quantity. All right. It is not this value because that would be redundant. Right? So this is how many bits are needed to represent the next part, and this is how many bits are needed to represent the next part. Is that clear? It's a good point. So to represent n in using the least number of bits, I need floor of log n plus 1 bits. That's the third part of the binary representation. What about the second part of the binary representation? I need to represent this quantity in binary. All right, which is basically floor of log of this plus 1 bits. Right? And then I need to represent this quantity in unary. How many bits do I need for that? Exactly the same number. So this is 2 times this particular quantity. What do you mean plus 1? Ah, okay. Whole thing times 2. Okay. So how large is this going to be? This is at most log n plus 1 plus 2 log n plus 1 plus 2 bits, right, which is basically log n plus 2 log n plus some constant. So for large n, basically we're using almost log n bits, which is the best you can possibly do. Right? You can't represent a positive integer n using fewer than log n bits. So the additional overhead that you are paying is just roughly 2 log n. Now if you wanted to give a more efficient representation, you could still go ahead because you can use the same process recursively. Right? In this case, what did we do? We looked at the binary representation of n, then the binary representation of the number of bits required in the binary representation, so the binary representation of log n, and then this required roughly log n bits, and then we looked at the unary representation of log n. But instead, I could look at the binary representation of log n and then represent that and do this in a recursive fashion. So basically, I could bring this quantity down to log n plus log n plus log n plus and so on and so forth. Okay, if I wanted to, I could do it, but this is good enough for our purposes. Okay. So one thing you have to note is that I can't, so let's say that if you think about this, this is a 3-stage representation of the integer n, right? The representation of n using log n bits, representation of log n using log n bits, and the representation of log n in unary. Now, what if I just represented n using log n bits and log n using unary? How many bits would I require? So roughly 2 log n bits. Okay, but to me that is going to be too much because I want something that grows only as log n and not as 2 log n. Okay. So I can bring this down to log n plus log n plus log n and so on. If I try to cut it even shorter, in the sense that if I reduce the number of stages, so to speak, then this would come down from log n. This would go, the number of bits required would go up from log n to 2 log n, roughly 2 log n. But I don't want to do that. I want something which grows as log n plus something that is much smaller than log n. All right, so that's the trick. Any questions so far? Okay. So now we have a representation of any integer using roughly log n bits. And we're going to use this to represent both the length and the pointer. All right. So let's try to put things in perspective. Let's take this example. let's say this is the string. Okay, ABC, ABC, ABC. Okay, let's try to get the Lempel-Ziv compressed string for this particular sequence. The first stage is you find the LZ77 parsing, right? Which in this case is going to be A, B, C, and then ABC, ABC. What is the encoding of this? It is 0, comma A, 0, comma B, 0, comma C, 1, 3, and 6. Right? So how do you represent this? Let's say that the alphabet size is 3. Okay, we know that the alphabet, both the encoder and the decoder know that this is the alphabet. So I can represent this using 2 bits effectively. And let's say that they're represented as 0, 0, 0, 1, and 1, 0. So the binary representation of A is 0, 0, binary representation of B is 0, 1, and binary representation of C is 1, 0. So what would be the compressed string? This is 0 followed by 0, 0, and then 0 followed by 0, 1, and then 0 followed by 1, 0, and then I have 1. Now I need to look at the encoding of 3, the integer 3, which would be 1, 1, this is represented using 2 bits, 1, 0, 0, 1, followed by the representation of 6, which is 1, 1, 0. This is represented using 3 bits, so 1, 1, and 0, 1. So this would be the compressed version of this particular sequence. Right? Seems rather elaborate and it looks complex. It doesn't even seem as though you got any compression. It looks like you only have a longer string. All right. But okay, I leave it as an exercise for you to try to decode this using the LZ77 decoder. So start from the left. You know that the first bit is the flag bit. So that's 0 followed by the first character, which is represented using 2 bits, and then flag bit 0 followed by 0, 1, 0 followed by 1, 0, and then flag bit, and then the binary representations. All right. So why does this achieve any form of compression at all, and how good can this get? Now, I will not derive the rate of this scheme. It's a fairly complex proof. As you can see, the scheme itself is not very straightforward. It's not very intuitive at all. But still, I'll try to give some insight as to why this can even approach the entropy rate. So firstly, let's try to think about what can happen in each phrase. As in, which phrases contribute to most of the rate, so to speak, or the expected, or the length of the compressed string. Now there are 2 types of phrases. Right, the first, which is a new character. Okay. So if there is a new character, then how many bits do you need to represent this particular phrase?
2. 1 plus log 2.
1 plus log of the cardinality of x. The flag bit plus these many bits are required. But then you will not see too many characters anyway, right? Because the total number of characters is the size of the alphabet. Relative to n, these kind of phrases are going to be very small. You will see at most cardinality of x, many such phrases. So this contributes a very small part to the length of the compressed sequence. So this is nothing to worry about. The remaining consists of the flag bit, the pointer, and the length of the match. How large can these be? So in this case, this requires 1 plus log of whatever, approximately log of the pointer length plus log L plus order log P plus order log N. So this is the number of bits that are required to represent each of the other phrases. Now all of these are random quantities, right? Because the string is random, therefore P is going to be a random quantity, L is going to be a random quantity. Now how large can P be? Okay, it turns out that among these two, the pointer is going to dominate the length. The number of bits required to represent the pointer on an average is going to be much more than the number of bits required to represent the match. All right? Which is a bit intuitive. All right? Because if you take let's say a random string, assume that it's an IID string, you will not see very long matches. And potentially you may have to travel far back to find a match, to find the longest match. So among these two, this turns out to dominate. So how large can this be? So for convenience, let's assume that for understanding, suppose that the string is IID. Okay, just to keep things simple. So I have this sequence x0, x1, x2, and so on. Let's say that we are currently, I've just, I have let's say a string of this form. So consider this IID process, which goes infinitely far to the left and infinitely far to the right. Okay, it's a simplification, and this is, and each of these symbols is IID drawn according to Px, the distribution that generates the source. And assume that we have parsed everything up to x minus 1, and we want to find the longest match from x0 and so on. Okay. Just for convenience, let's suppose that x0 we'll look at an even simpler problem, which is the following. How far back should you go to find just the symbol x0. So it's a sequence of symbols, and I have x0. I want to match just x0. Let's not worry about finding the longest phrase and so on. When was the first time in the past that you saw x0 traveling backwards? It turns out, so let's say maybe I need something else. Let's say that rho x0 is basically the smallest I such that x minus I is equal to x0. So if I have something like A, B, C, A, B, C, A, say that this is my x0, then rho x0, the first occurrence traveling to the left is here, right? So in this case, rho x0 would be 1, 2, 3, 4. So how large can rho x0 be? Or in expectation, how much is rho x0? You can show that expectation of log of rho x0, this is equal to, let me log of given that say x0 is equal to x, this quantity is log 1 over px of x. All right. So what is this quantity? It is basically the number of bits that are needed to represent the pointer for x0. Right? This is the number of bits needed to represent the pointer for x0, and conditioned on x0 being equal to x, the number of bits required for the pointer is log 1 by p of x. So on average, how many bits do I need to represent the pointer? It is expectation of okay, I'm sorry. There is this is not equal to, but rather this is only less than or equal to. Okay, it's an upper bound. So what is the expected number of bits needed to represent the pointer? It's equal to the entropy, right? Or it's less than or equal to the entropy. I mean, even proving this statement is not very easy, requires a little bit of detailed analysis. And this only tells you how long you find, how far back you have to go to find the first match. We still haven't gotten to phrases yet. All right, so that requires an additional intricate analysis. But in the end, what you can show is that the total expected number of bits to represent all the pointers is roughly n times say n times, assuming that it's IID, this would be n times h of x into 1 plus little of 1. And you also need to show that the expected number of bits to represent all the lengths is in fact much smaller than n. All right. I'm sorry? N is the length of the source sequence for large enough n. So the overall expected length xn is roughly equal to the entropy, or more generally it's actually going to be h of xn into 1 plus little of 1. It seems a bit counterintuitive, but in fact you can prove this. If you're interested in looking at the whole proof, it's there in the Coer and Thomas textbook. But yeah, there are quite a lot of steps in the proof. In fact, this is exactly what is used in many algorithms like zip. And from this, you can also see that if you take a small file and try to compress, then you don't get any form of compression. In fact, the so-called compressed file is going to be longer than your source file. You can run this experiment. Take let's say a file which has 1 or 2 bytes. Just take an empty text file, type let's say 1 or 2 characters, compress that using zip. You'll see that the zip file will be longer than, will take more space than your original file. So all of this works well only if your if the length of the source sequence is large enough. So this approaches entropy, but the rate at which it approaches entropy is rather slow. But this is by far the standard used for text compression. Right? Any questions? Okay. So now, just as we had LZ77, the LZ78 algorithm works in a very similar fashion, except that the way you parse these sequences is different. So in the LZ78 parsing, so assume that parsed x1 through xt. The next phrase is basically the shortest substring x t plus 1 up to x t plus k that is not a phrase in the context. So how does this work? Let's again take maybe the example ABC, ABC, ABC. So if it's a new character, then that's going to be a phrase. So you have A, then you see the next character, which is B. The next character again has not been seen in the past. So it's C. Now what about the next phrase? The next phrase should be something, it's the shortest substring that is not a phrase in the past. Let's see the next character A. Is A a phrase? The previous phrase? Yes. What about AB? AB is not a phrase. AB is a substring that you have seen in the past, but AB is not a phrase that you have seen in the past. So the next phrase is just going to be AB. All right. What about the next? So C. Is C a phrase? Yes. CA. CA is not a phrase that's been seen in the past. So it's just CA. And then is B a phrase? Yes. Is BC a phrase? No. So the next phrase is just BC. Right, so this is another way of parsing. This is the Lempel-Ziv 78 parsing. Now if you think about it, in this particular form of parsing, each phrase is basically a previous phrase plus some character. Right? Because in this case, because that is the shortest possible phrase which has not been seen in the past. So the shortest possible phrase not seen in the past must be some phrase that you have seen in the past plus some character that was not part of that particular phrase. All right. So the encoding is basically each phrase. There's only one kind of phrase in LZ78, and the encoding is just you need to say which phrase this matched with in the past, and then you have to say which character it is. So if we go back to this example, A, B, C, A, B, C, A, B, C, the parsing is A, B, C, A, B, C, A, and B, C. The encoding would be, okay, there's no pointer to a previous phrase, so let's just represent that using a null pointer. and then the character A, the null character pointer and B, the null pointer character C, and then A, right? So you need to provide a pointer to which phrase this matched with. So A was a previous phrase, but AB was not a previous phrase. So A is basically the first phrase followed by the character B. Similarly, the next phrase is CA. In this case, C was a phrase seen in the past, and A is the next character. C was the third phrase, so you'll represent this as 3, comma A. And the last phrase is BC, where B was a previous phrase and BC was not a previous phrase. So B was the second phrase, followed by C. So this would be the LZ78. You can use a relative pointer if you want, but you can use an absolute pointer also in this case. Again, there are minor variants that you can look at, but all of them will essentially give you the same expected length, at least up to the first order. All right. So this is basically the LZ78 encoding, and you know how to represent all of this in binary already. All right. So each phrase consists of an integer and a character. So you represent basically the pointer using the prefix-free code that we've seen previously. But now you have a character in each phrase. Right? So one way is you just represent the character using log cardinality of x bits. But since these characters repeat so often, you might as well encode them a little more efficiently. So for example, you could use a Huffman code or an arithmetic code based on the frequency of occurrence of the characters. All right? Just the first order entropy. Represent the character using whatever Huffman or arithmetic code. Huffman code is by far the most popular way of encoding this character. All right. So essentially, if you take most of these compression tools, be it zip, 7-zip, or the Unix compress, all of them use either LZ77 or LZ78. In fact, these are also used for other types of compression. For example, if you take GIF, the format used to represent images or sequences of images. So GIF uses LZ78. Unix compress uses LZ78. Zip, 7-zip, most of them use LZ77. Right. There are, of course, a lot of optimizations done. How do you choose the window length? How do you represent each of these in a slightly better format, and so on, which can give rise to a lot of improvements. All right. Any questions? Okay, let's have a quick quiz.